We have here a classic physics problem. It's a vector application. There's a weight hanging from a ceiling. We've got two wires supporting it. We're going to try to figure out the tension in each of those wires. There's not a whole lot I'm given. Just want to draw your attention to what we are given. We're told one of the angles is 70 degrees, another angle is 37 degrees, and the total weight of the prop is 125 degrees. We want to know what's the tension in each of the wires. Well, if you take a look at the picture that I drew here, I'm going to treat this from a mathematics point of view, not a physics point of view. If you're in a physics class, you're used to the physics way of force diagrams. I actually prefer that. I was trained that way. And they're a little more casual about the direction that forces are going in. And they just use a little common sense and say, okay, these balance out, and so on. The mathematician way is a little more rigorous in terms of really tracking all the angles relative to a positive x-axis, what the plus and minus signs are, and so on. Because this is a math class, we're going to do it the math way. But by all means, if you're used to the physics way and you know how to do it that way, go ahead. So as we study vectors, we know that the magnitude of each of these vectors is just a number. It's a scalar. And the angle of each of these vectors is really important for finding those components in the directions of x and y. So if you look at these, this diagram that I've made, notice that 37 degrees right here. Okay, that's pretty easy. We can see why that's 37 degrees based on what's on the ceiling. But this one might actually surprise you. The angle of u is 110 degrees. Okay, what I care about is not this angle of 70 degrees. That is 70 degrees, but what I care about is that angle relative to the positive x-axis. Okay, that's 110 degrees. And when I say relative to the positive x-axis, this is what I mean, this angle right here. Okay, that's the one we have to use for our math. And likewise for w, I'm going to use that angle that wraps all the way around. Okay, I'm not going to say this just straight down. I'm going to use this angle of 270 degrees right there. So that's the reason for some of these things over here. They might surprise you a little, and that's the key to this problem if you're using vectors. So let's write some equations. I know the weight is not moving in either direction, so I can say this. I'm going to use the vectors in the diagram. Ux, which is the component of u in the x direction, plus vx, which is the component of v in the x direction, plus wx, which is the component of the weight in the x direction, has to be 0. The net force on this object is 0, so we add all these forces together, and it's not going to be moving left and right. Well, let's go ahead and figure out what these things are. Ux is going to be the magnitude of u times the cosine of its angle, 110 degrees. Vx is going to be the magnitude of v times the cosine of its angle, which is, let's see, what was that, 37 degrees. That's the one on the right. And then we have the magnitude of w times the cosine of its angle, which is 270 degrees. And this all equals 0, so I'm running out of room there. Now, the nice thing about the weight going straight down is we know the cosine of 270 is just 0. So that term cancels out, and we can stop worrying about that. If I simplify the rest of these, look what I get. Negative 0.342. With some more decimals, you're going to have to keep track of more decimals than I am, because you're the one getting graded on this assignment. But we've got negative 0.342 times the magnitude of u plus cosine of 37 degrees. That is 0.799 times the magnitude of v. Okay, that equals 0. Now, if I simplify this a little more, you can see I'm just going to isolate the magnitude of u and write it in terms of v. So I'm going to subtract v to the other side. If this is not clear, just go ahead and pause the video, take a moment to convince yourself of the algebra, but this is basic algebra right here. So I say the magnitude of u equals this division problem times the magnitude of v. And let's write that a little more simplified right here. The magnitude of u is therefore equal to 2.336 times the magnitude of v. Now, I'm making rounding errors here, I know that, and our final answer is going to be a little off. But why don't we just put this in a box and hold on to that for now. We're going to come back to that later. We're going to call that equation 1. Now, let's talk about the y direction. In the y direction, very similar balance of forces. It's not moving up or down. But this time, the weight is going to matter because that is going straight up and down here. So what do we got here? Let's see. Very similar to the x direction, except now instead of cosines, I'm dealing with sines. So I've got the magnitude of u times the cosine of its angle, the sine of its angle, 110 degrees, magnitude of v times the sine of its angle. See the same angles. We're just using the sine components for y. And I just noticed I did not write y there. Let's get that fixed. Okay. Plus the magnitude of w, which times the sine of 270 degrees. It's going to work out very nice. And this is our force balance diagram right here. Well, let's do all the math here. Let's see, sine of 110 degrees. That's pretty big. That's 0.940 times magnitude of u. Plus sine of 37 degrees. That's not as big. That's 0.602 times the magnitude of v. Plus, now the sine of 270, this might throw you off a little bit. Sine of 270 is a negative number. If you remember your unit circle, that's just -1. So I get minus 125 here. Because remember, the magnitude of the weight vector is 125. That's how many pounds the prop is. So if I rearrange this a little bit, what I want to do now is take equation 1 from above and substitute that in right here. And I'll show you, I'll just use some colored ink here to, what did I have is, I don't even know what those colors anymore. Let's just use green. This is going to be 0.94 times 2.336 magnitude of v. Okay, and then I'm going to continue on with the rest of that equation as it was. 0.602 magnitude of v minus 125 equals 0. Now, there's some algebra here, but I want you to not worry about the ugly numbers. There's some gross numbers, but I just want you to focus on the fact that I've got a variable of the same letter, so those are the same thing, and that's it. Everything else is numbers. There's only one variable in this equation, so I'm going to combine like terms. First, I multiply the things on the left. I'm going to multiply those together, and then I'm going to add this one, and I'm going to get, let's see, what do we get? I'm skipping some of the math here, because I'm assuming you can do some basic algebra. 2.798 magnitude of v equals 125. Now, if I lost you on that step, pause the video, convince yourself that this is true, and I'm going to divide each side by 2.798, and look what we get. The magnitude of v, the tension in that wire, is 44.67 pounds. Okay, so that's an answer. That's like one of the answers to the question. What is the weight? Now, I'm off. I know I'm off a little bit because I made some rounding errors up above, right? I only used 4 digits. If you want to use like 5 or 6 digits, you'll be more precise than I am. But now what I'm going to do is I'm going to plug this into that equation, okay? The way I'm going to do that is I'm going to just write this. I'm going to take equation 1 again. Magnitude of the u vector equals 2.336 times 44.67. Okay, I'm going to plug this right in that parentheses. And what I get is the tension in that wire, magnitude of the u vector, which in this case is 104.36 pounds. Now, at this, I always like doing a sanity check at the end of a physics problem. Does this make sense? Does it make sense that vector u is much larger than vector v in their magnitudes? Well, take a look at your diagram. U is a vertical wire, almost vertical. V is kind of off to the side. It makes sense that u is going to be supporting more of the weight since it's closer to the center of this brick or whatever this object is. It's carrying more of the weight of it. So this is the vector approach. Hope you enjoyed it. We'll get lots of practice of this going forward.